and we decorated them with many elements, and that gave us a kind of a lot of structures. So how do you then evaluate the thermodynamic stability computationally? So basically we do DFT calculations, and we calculate formation energy, and we perform phase stability analysis, right? And after doing this analysis, it can give us new thermodynamically stable compounds. Okay, so before generating new structures, we are very careful. So because we didn't want to generate any random structures, right? Because the possibilities would be very very high, because if you take 100, even 100 elements from the periodic table, and if you put it in the four sides, so the number of combinations would be 100, C4, and which is a very large number. So we didn't want to explore all those compounds. So therefore we constrained our search space with some criteria, and this criteria we have deduced by studying the already known compounds in this family. Mainly we saw that the A site can be occupied by these elements, meaning the first column and the second column, which are alkali metals and alkaline earth metal. The second and the third site can be occupied by this transition metal, and the last site, the Q site, can be occupied by this chalcogen, right? So basically we only constrained the new compounds while generating the new compounds with these rules. So that kind of gave us a constant search space. So after doing generating new compounds, so we got about 5,000 new compounds, and then we perform their DFT calculations, we perform phase stability analysis, and after doing all of this, it gave us about 600 new compounds. Now this number is really significant, because if you look at existing databases, and if you look at already known compounds that people often talk about, for example Heuslers, right, or perovskites, the total number of known stable Heuslers or number of known stable perovskites are actually low. So for example, in this family, this quaternary AMM Q3 family, the number we have discovered about 800, right? But in the full Heusler and the half Heusler, they are 600 and 1100 and so on. But Heuslers are being studied for over 50 years, right? So compared to that, this number is really significant. So that means we have discovered new compounds in a family which people haven't looked earlier much. Okay, so then our aim is to find low thermal conductivity semiconductors that we have already mentioned earlier. So therefore, so these are already semiconductors, because that is how we have chosen the compounds from the newly discovered list, and then we wanted to evaluate its thermal conductivity. So to calculate thermal conductivity, we have solved the semi-classical Boltzmann transport equations, and then we have plotted the thermal conductivity, and we found that the thermal conductivity values are very low. The highest value is about 3 watt per meter Kelvin at room temperature. So this is generally considered to be a low thermal conductivity semiconductors, right? So after discovering these 600 compounds, we didn't stop there, because the number the search space is actually very huge, and we constrained ourselves to generate only 5,000 compounds. So how can we explore the other compounds that we haven't considered, right? So now so because if we remove the constraint, right, like this, and if we put all elements at all sites in every possible combinations, the number would become a million, right? About 800,000. So how would we choose this how would we perform DFT calculations on 800,000 compounds and perform the stable compounds? So it is very very computational challenging task. So thanks to machine learning, which came to the rescue, right? So we can apply machine learning to screen the stability for these 800,000 or close to 1 million compounds, and then it can give us new compounds which would be thermodynamically stable. So let's see, so what machine learning model we developed. So this is a model which we developed, which is called scale invariant crystal graph convolution neural network. So this is a graph neural network model, and this is scale invariant, right? So many of you probably are familiar with graph neural network models. So in a graph neural network, we represent the crystal structure in a graph, right? So in a graph you have nodes, and between the nodes you have edges, right? So you can represent a material, the atoms in a material, like a graph, and the bonds between the atoms like a edges between the graphs. So that is how we can represent the material, and then you can embed the graph with the properties of those atoms and the materials. So basically so this type of model are physics informed model, because you encode the physics informations of the materials into the graph object. And so we first convert the crystal structure into a graph object, embed with the informations of the atoms, and then we feed this graph object to the neural network model, and then the neural network model is trained based on a particular property. So in our case, we wanted to predict the stability of the compound. So, and for which we need the formation energy. So basically, we train this graph neural network model to predict the formation energy of those billion compounds, right? So this is how our model is in schematically. And then so our model is also multi objective, meaning we can get multiple property at the same time. So here we are getting formation energy as an output, and we are also getting relaxed volume of the structures. So meaning many of you have done DFT calculations, and you know that to calculate any property, first you have to relax the structure, right? If you don't relax it, the properties would be wrong, right? But here, so typically when you train machine learning model, you need to feed the model with relaxed structure, right? So again, you see, if you want to train the model with with thousands of compounds with relaxation, right? It would take a lot of computational time to relax the structure and then feed the structures to the model. So here we developed an approach where we can just feed the unrelaxed structure and then train the model, right? And it can predict the property as if it were seeing relaxed structure. So that is why this is a scale invariant model, and it is giving us multiple properties, meaning formation energy, which is the property of interest, and the relaxed volume. So this is multi-objective. So we applied this model to those 800,000 compounds, and then it predicted about 8,000 stable compounds. So this is the machine learning predictions, right? And then we did further screening to remove some radioactive elements and so on, and then ultimately we came up with about 4,000 compounds. Now again we have to do the same thing. So we have to do DFT calculations on these 4,000 compounds, and then we have to perform stability analysis, and then ultimately it gave us about 100 compounds. Now the difference, the new compounds that we discovered in this project is slightly different from that I showed you earlier. So these compounds are unconventional, right? And unconventional, rightly so, because we have removed the constraints that we have earlier that we have applied earlier. So meaning, if you look at the compounds, these elements are not following the rule that the experimentally known compounds followed. Meaning, any element can occupy any site, right? So for example, here the first two elements are both alkali metal, right? And the second compound, the first element is alkali earth, and second is also alkaline earth. So basically, so these kind of are unconventional compounds that we would not even think about if we not had we not applied the machine learning model. So this is the beauty of the applying machine learning model to discover completely new compounds that we could not even think of before. And again, we randomly selected some compounds from the predicted list, and then we calculated thermal conductivity using again Boltzmann transport equations, and the thermal conductivity is also very low. So these are also semiconducting compounds, and so this is this paper is reported here. Okay, so now one would say that you have discovered so many compounds. So now what? Where are the experimental validations? So that is a big challenge, right? Whenever people do something experiment computationally and theoretically, there is always a questions from the experimental side that we predict so many interesting things, so many things, but where is the experimental validations? So here is the validations. So we predicted about 800 total compounds, and after our predictions in the last 5 years or so, about 60 compounds have been experimentally synthesized by different groups. So these are some compounds that I am giving, but there are few more compounds that are not present in the list. So this is the validation of our predictions using high throughput computational methods and machine learning. Okay, so after discovering this, we also didn't stop there. So we wanted to find materials in the same family for different applications. So we choose so we wanted to see whether we can get new photovoltaics materials among the known compounds that in this family. So to discover photovoltaics compound, first we surveyed literature, and this is a plot of photovoltaic efficiency versus uh, DFT calculated band gap, effective mass, and so on. So these are all experimentally known photovoltaics material, and this efficiency is the experimentally measured efficiency. So from this analysis, and there are a few other analyses that we have done, we wanted to get some criteria, some screening criteria. So basically, the idea is that we would choose some criteria based on the existing data, and then we would apply this screening criteria and discover new compounds. So we found that materials for which the band gap is between 0.5 and 1.5, they would be good photovoltaics, and the effective masses, if they are below 1.5 m0, m0 is the free electron mass, they would be good photovoltaics. So apply screening the criteria. We have, this is kind of the funnel diagram. We started with all the experimentally known compounds, not theoretically predicted compounds, right? And then we successively screened the criteria, and then we found about 14 compounds, and which has direct band gaps, and 32 compounds which have indirect band gaps, but they fit the criteria to be good photovoltaics material. So from this list, we selected 4 compounds for detailed study, and then we calculated band structure, which is direct and parabolic band gap, and the band gaps are in the range of ideal photovoltaics. We performed, we performed the absorption efficiency calculations, and the theoretical photovoltaic efficiency calculations, which all shows good values. We calculated exciton binding energy. So exciton binding energies are quite low. That means, the electron hole pair can be separated quite easily. So that means, that also says that these compounds are potentially very good photovoltaics material. Further, we performed time dependent density functional theory calculations to see the carrier recombination rate. So that is a very important factor for photovoltaics material, because if the electrons and the holes, combine very fast, so then we cannot separate it out. So that means the photovoltaic efficiency will be very less. So the longer the carrier recombination time, the better it is, because it gives you a lot of time to separate the carriers and get a voltage. So for this compound, from the TDDFT calculations, the carrier recombination rate, is quite large. This is larger than even the known halide perovskite, or in the similar range. So that also shows that, these compounds are quite good. Uh, and we have also performed defect analysis to see whether there would be any unwarranted defects within the band gap, because if there are unwarranted defects, it can trap the charge carriers, and then it can again deteriorate the efficiency. So here, from the charge defect calculations, we didn't find any defect states within the band gap. So there is no deep defect states, which is also good news for these compounds. Okay. So ultimately, so materials discovery is very important, but it requires synergy between experiment and theory or computations, right? Because computations alone, if they predict and the predictions just stay in paper, it doesn't have any effect, right? So basically, there needs to be synergy between experiment and theory, and only then, real discovery will happen, and it would be very impactful for the science and society. So therefore, I envision a system where, we can combine both experiment and theory, and it would work in a closed loop cycle. So the feedback from theory would be given to experiment, then experiment will analyze data, and then based on the data, we will adjust our, decision making protocols and modify our simulations protocols, or, like theory protocols, and then we would do this in a loop, and that way we will get a kind of good predictions, and also the predictions would be synthesized in laboratory and tested in laboratory. So with this, I thank you, and I'd be happy to take any questions.
I had a very nice question that the descriptors that you use to find whether the material is what you want or not, are they theoretically calculated from some are they calculated from some theory, or are they found out by fitting the data that from the material data?
It is actually both. So for example, the first work that I showed, to discover new low thermal conductivity semiconductors, we looked at the ratios of the B max to B mean, right? So the B are anisotropic displacement parameters, which are already calculated by any experimental groups which synthesize new crystals, right? And those informations are written already in the CIF file, right? So that is the experimental data that we took. But also we calculated other quantities, for example, density of state near the Fermi level, right? The band gaps, those are calculated from DFT. So and then we combine both the informations, and yeah, and then we applied the filter on those materials.
And did you do other stability analysis apart from thermodynamics, like the mechanical stability or static and dynamic stability of the material?
So dynamic stability, yes, like the phonons. So yeah, the compounds that I showed, they're all thermodynamically, like both dynamically stable, like the phonons are stable, and the thermodynamically stable. But mechanical, we haven't tested.
Hi, Kaushik. It's always great to listen to your talk. I had out of many other interesting things. One thing which caught my attention was you implemented a trick which helps you save some time by not letting the material to relax fully.
Right.
So If possible, in short, can you, like, how much time could you save per material with that? And if possible, can you explain
It's a
that?
lot. So for example, let's say if you have a 10 atom unit cell, right, and to relax it, right, in typical small computer using like 4 5 or 8 cores, it can take you 30 minutes, right? So now imagine you are training the model on 100,000 compound, so you multiply the 100,000 with 30 minutes, so that saves you a lot of time.
Okay. Any other question, comments? If not, let's thank Kaushik.
Thank you.